Have you ever actually stopped to think about what happens the exact second you click a link or hit send on a message? In that tiny fraction of a second, an incredibly complex, totally invisible ballet of protocols, models, and hardware goes to work. It is a beautifully orchestrated system operating entirely behind the scenes to deliver your data flawlessly across the globe. So today in this explainer, we're going to pull back the curtain and make that invisible ballet visible.
All right, let's just quickly look at our roadmap for today. We'll be covering 1. The blueprints of networking. 2. Directing local traffic. 3. Navigating global networks. 4. The art of routing. And finally, 5. Managing network devices.
Section 1. The blueprints of networking, understanding the universal rules.
At the very foundation of all networking rules is the OSI reference model. This is a genuinely brilliant 7-layer conceptual framework. It takes the absolutely massive task of network communication and breaks it down into distinct logical layers. It starts all the way at the bottom with layer 1, the physical layer, so think cables and electrical bits, and it moves all the way up to layer 7, the application layer, which is what you and I actually interact with on our screens. This blueprint is absolutely crucial because it ensures that completely different systems built by entirely different manufacturers can universally communicate. It's literally like the rules of grammar for computers. Without them, no one would understand anyone else.
Now, a comparison perfectly illustrates the evolution of those rules. We have our classic 7-layer OSI model, but we also have the newer 5-layer TCP/IP model. While the OSI model is highly detailed and fantastic for learning the theory, the TCP/IP model is what the modern internet actually runs on. It essentially condenses the top layers into a single application layer, making the whole shebang just a bit more streamlined. So, now that we have our theoretical map established, let's jump into the hardware that brings these layers to life.
Section 2. Directing local traffic inside Layer 2.
Okay, so to really grasp Layer 2, we need to talk about the ultimate local traffic cop, the network switch. And it's super important to contrast switches with routers here. Switches operate at Layer 2. They use MAC addresses to forward frames locally, basically connecting devices that are sitting in the exact same network. They are designed for pure, unadulterated speed. Routers, on the other hand, operate at Layer 3. They use IP addresses to navigate globally between entirely different networks. Also, and this is a big one, if there's a loud broadcast message sent to everyone on the network, a switch just forwards it right along, but a router strictly stops it from leaving the local neighborhood.
It's actually pretty wild how a switch manages all that local traffic. It does it by building something called a MAC address table. The switch actively learns the unique MAC address of every connected device and maps it to a specific physical port, like port 1, 2, or 3. Why go through all that trouble? Well, if the switch didn't do this, it would literally have to shout every single piece of data out of every single port just to reach one computer. That would cause massive, network-crushing congestion. So this table is what prevents total network chaos.
But how does the switch physically move that data once it knows where it's going? Well, it generally uses one of two forwarding methods. The first is store and forward, where the switch cautiously receives the entire data frame and runs a mathematical formula called a CRC. This checks for errors before sending it on. It's incredibly safe, but it takes a split second longer. The alternative is cut-through switching. This method just grabs the destination address and starts forwarding the data immediately, prioritizing lightning-fast speed over strict error checking.
Section 3. Navigating global networks, entering Layer 3.
So, if Layer 2 MAC addresses are basically your device's permanent physical fingerprints, Layer 3 uses the IP address. This is a 32-bit logical address. Think of it as a digital postal code. It's exactly what allows your data to pack its bags, leave the local switch, and find its way to a server sitting halfway across the globe.
Which brings us to a really fascinating puzzle. The internet is made of billions of interconnected devices and millions of possible pathways. So how on earth does a router, the device responsible for looking at that IP address, know exactly which path to choose to send your data across the vast internet?
Section 4. The art of routing, finding the optimal path.
Okay, so the crucial point here is that routers essentially learn these paths in one of two ways. First up, we have static routes. This is where a human network administrator physically types the exact path into the router. It's completely manual. Then on the flip side, we have dynamic routes. This approach uses clever protocols like OSPF or EIGRP that allow routers to actually talk to each other. They can automatically adjust to topology changes or link failures without any human intervention whatsoever.
Now, you might be wondering, if dynamic routing is totally automatic, why would anyone ever use static routing? Well, static routing has some very distinct trade-offs. Because the route never changes, it takes zero CPU power from the router, uses no extra bandwidth, and is incredibly secure since the admin explicitly controls the flow of traffic. But the massive downside? It absolutely does not scale. If a new network is added, an administrator has to manually update every single router by hand. In a large enterprise network, that is a full-time nightmare.
And here is what that actually looks like under the hood. Take a classic static route command. By typing IP route followed by the destination network and a subnet mask, the administrator is explicitly telling router A, hey, if you want to reach network 172.16.1.0, you must throw the data over to the next hop IP address of 172.16.3.2. It is rigid, it's precise, and it is completely manual.
But wait, what happens if a router receives an IP address that it just doesn't have a specific route for? Normally, it would just drop the packet entirely. Gone. To prevent these data black holes, we use what's called a default route. Think of this as the router's path of last resort. It basically tells the router, look, if you don't know where to send this data, just send it out this specific door and cross your fingers that the next router knows what to do. However, you have to be careful, because if those default routes are configured poorly, you run into a really severe danger, a routing loop. Just imagine what happens when router A doesn't know a destination and uses its default route to send the data over to router B. But router B doesn't know it either, and its default route points right back to router A. Suddenly, your data is a trapped pinball, endlessly bouncing back and forth until the network is completely brought to its knees. To handle massive amounts of routing without buckling under the pressure, modern hardware uses some incredibly clever tricks, like Cisco Express Forwarding, or CEF. Instead of stopping to calculate a path every single time a new packet arrives, CEF proactively computes all that math ahead of time. It bakes those optimized routes directly into the hardware tables. This drastically lowers CPU overhead and allows data to flow at lightning-fast hardware speeds. A real game changer. And finally, Section 5. Managing network devices, accessing the Cisco IOS. So, to actually configure these devices, you interact with the Cisco IOS, the Internet Operating System. You generally access this in three ways. First is console access, where you literally take a physical cable and plug your laptop directly into the device itself. The next two are remote, over the network, Telnet and SSH. Now, Telnet is incredibly outdated because it sends all your passwords in plain, totally readable text over the network. SSH, on the other hand, is the modern standard, using secure cryptography to hide your traffic. Seriously, always use SSH.
Once you are securely logged in, you're going to want to jump straight into configuring the physical ports. For a switch, you'll dictate the port mode, deciding whether it's connecting to a single PC or trunking lots of data to another switch. You'll set the duplex, ensuring devices can send and receive data simultaneously without crashing into each other, and you'll lock in the speed, optimizing for the absolute fastest data transmission rate possible. And wow, that brings us right back full circle. Every single time you stream a video or open a web page, you are relying on MAC address tables directing local frames, static and dynamic routes navigating global IPs, and hardware-accelerated routing keeping everything moving instantly. So I'll leave you with this. Now that you can actually visualize this invisible ballet, how does knowing about this hidden, perfectly orchestrated infrastructure change the way you look at your everyday digital life? Thanks for exploring this fascinating system with me today, and as always, keep questioning how the world around you actually works.